Okay, so in the previous class, what we were discussing about was about the non-parametric density estimation and how different kernels could be used for the density estimation of the non-parametric, PDF or the probability density function. And we were also looking at the mean shift algorithm or the mean shift procedure, which can be used to find which is the densest point given a data point distribution, right? So in today's class, we'll continue with the tracking using the summary matching. So let us assume that you've been given a frame, okay? And the region of interest or the domain of interest that we have is a circle of a fixed radius and whose center is at a pixel location which is given by y, let's say. Okay, so we are just assuming some kind of, let's say you have an image, okay, and you have a particular object over here, and you are assuming a circular domain of interest, and the center of that particular circle is located at the pixel location y. Okay, now the circle, the particular circle, circular domain what we are considering will have a fixed radius, and when you say in the next frame if the object has moved, what we assume is that the circular domain has the same radius, but it must have changed the center, the location of the center of the circle. That means if, let's say, the person has moved right towards this side, accordingly the circular domain also shifts to the right side. Okay, so basically in that shifting what happens is only the location of the center would have moved. Okay, so it is the center or center of the domain, which is basically the value of y. Okay, given y is the center of the circular domain, then the value of y would be changing. So let's say for a current frame that you're considering, if the center is at a location y, for the next frame you may have to calculate the new center, and let's say that is given by y new, or maybe you can give it as yu for y updated or so on. Okay, so it would be the new location of the center that can be calculated, right? And so our aim would be to find this particular y. Okay, that is the same as given over here, find dn plus 1. Okay, basically that means if you are translating it in terms of a mean shift procedure, then what you're doing is in the next frame you have to find dn plus 1 whose histogram is similar to that of dn. So what we assume is, given if you are trying to calculate the histogram of this circular domain of interest, okay, then that histogram, and let's say it has translated to this particular location, right? The histogram of this new location of the circular domain will also be the same, or it will be similar. So what we do is we use the mean shift procedure to find the new position for y. Okay, this new position of the y updated or the y new, okay, in the next frame, such that the histogram of the frame is similar to that of the previous frame, which is given by, let's say, dn. Okay. Let us consider an example over here. So let's say this is our first frame, and in this first frame you have this red circle. Okay, circle in the sense it's not exactly circular. We are just saying it's a almost circular domain of interest. Okay, and this is where our object lies, or basically it's a person who is playing the tennis, and this is our object of interest, or the domain of interest is this particular circular region. Okay, so what we do is, from this, so this is a model that we have chosen, and then from here we try to calculate a histogram for this. Okay, that is nothing but the probability density function that is being calculated. Now once you have the histogram, what we do next is we have to find out a similar histogram patch in the next frame, right? So let's say in order to find the histogram patch in the next frame, what we do is, so in this frame, this is the circular domain of interest. We assume a particular region of interest around the circular domain. That means instead of having to search for this circular domain, okay, throughout the whole of the image, what what you can do is you can consider a neighborhood around this in such a way that you need to only check within this neighborhood. So what we are assuming is that the domain of interest or the object that we are trying to track would not have moved much along a lot of distance between two consecutive frames. So if we make that assumption that between two consecutive frames the object has not moved much, okay, it's not like it has moved from one corner of the image to the other, no, it has only moved a little bit, then we can make this assumption that the neighboring we can consider a particular neighborhood within which you can search rather than searching for the whole for the whole image, okay, in the next frame. Okay, so what we do is in the next frame we try to locate the object only within this particular neighborhood. Okay, so that means we consider different circular patches. Now within this or within this, like this, we can consider all throughout the whole image. Okay, so it can be overlapping patches also. All throughout the whole frame we try to locate circular patches, and for all these circular patches we calculate what is the histogram, and then we try to see which is the histogram which is the most similar, right? So by looking at the histogram which gives the most similarity, we can say that yes, that is a region where you have the domain of interest. Okay, so what we are doing is we are trying to search for what is the new value for y, that is the center of the circular domain, the new value for this y, in such a way that the histogram of this new circular domain as well as the previous circular domain remains the same. Okay. So as I said earlier, what we do is, what we're trying to do here, our aim is to find y whose histogram is closest in the sense, the most similar, or it is matching the most with that of the histogram which is present at yn, that is the next frame that you have, right? Now, in order to do this, what you can do is you can consider a coefficient which is known as the Bhattacharya coefficient. Okay, it is basically Bhattacharya coefficient can be used for comparing two PDFs or the probability density functions. Okay, so the equation is given over here. Okay, rho of p of y and p of yn is basically the Bhattacharya coefficient. So what you're doing is you're comparing these two PDFs, that is p y of n, that is a probability density function when the circular center is at the pixel location y, and the probability density function when the center of the center of the circular domain that we are considering is at the location yn, that is a new position for y. Okay, so for these two PDFs you can try to calculate the Bhattacharya coefficient, okay, given by this particular expression over here, where you take the root of the product of these two probability functions and sum it over different values of u. Okay, so what you're trying to do here is, or what happens here is that this particular coefficient will give you 1 if the two distributions are same. That means if these two histograms are matching, okay, then it would give the maximum value you will get would be 1. Okay, and let's say if they are very different from each other, then it would tend to be 0. So the value of the coefficient will lie somewhere between 0 and 1, 1 being the maximum where it says that the histograms are matching perfectly, and 0 being the minimum where you say that the two histograms are very dissimilar, okay, or they are very different with each other. Okay, sorry. Now what that means is that here you can also define a distance function, okay, that is given the Bhattacharya coefficient. So as I said, what you're doing is you're trying to find out what is the coefficient, okay, if it is maximum or minimum, right? If it is maximum, then that means the two histograms are similar, right? So you can say this particularly this particular problem boils down to saying we need to maximize the Bhattacharya coefficient in order to ensure, or in order to find out that value of y for which the two distributions of the two histograms are similar. Okay, so by maximizing the coefficient, what we are trying to see is for what value of y will the Bhattacharya coefficient will give me the maximum value, then that means corresponding histograms would be similar. Okay, so it could be formulated as a maximization problem. Okay, in other words, instead of a maximization problem, it can be also formulated as a minimization problem if you write it this way. Okay, that is, if I calculate 1 minus rho of p of y comma p of yn, that means I take 1 minus the Bhattacharya coefficient over here and root it over. Okay, what I get would be what you call as the distance function. Okay, so this basically calculates how much is the distance between the two histograms. Okay, p of y and p of yn. Okay, so here when I'm calculating the distance here, what that means is if the distance is high, then they are dissimilar. Okay, if the distance is low, then that means they are very much similar to each other. Okay, so if I'm using the distance function for the calculation, then it becomes a minimization problem where you say that, okay, you want to find the value of y for which the distance is minimum, because if the distance is minimum, then it means that the histograms are closer or more similar to each other. Okay, so that is about the Bhattacharya coefficient. So, just to summarize once again, what we are doing is, let's say you have an initial frame, okay, and you have, this is the next frame that you're having, okay. And what I'm trying to do is, I'm trying to find out, there is a circular region of interest, or a circular domain is present over here, whose center is located at the location y, okay, and you have to find out where is given the histogram of this particular domain. Okay, where can you find a similar histogram, okay, such that in the corresponding domain, okay, which is given by, let's say, the center of which is given by yn. Okay, at the corresponding location of yn, you will have the histogram that matches the best, or which is similar to that of the initial frame. Okay, and this in order to find this, you can either use the Bhattacharya coefficient, try to maximize the Bhattacharya coefficient, okay, where it tries to see how similar the two probability density functions or the histograms are. Okay, or you can also formulate it as a minimization problem, where you try to calculate a distance which is given by root of 1 minus the Bhattacharya coefficient. Okay, and which means that if the distance is the lesser the distance, the most similar would be the two histograms. Okay, so in either of the case, either way, if you're maximizing the coefficient or you're trying to minimize this distance function, what you're trying to finally achieve is that you're trying to find the value of y for which the histograms are similar. Okay, and as I said earlier, we do that within a particular region of interest rather than the whole image. Okay, so as said earlier, in order to find y of n plus 1, what we do is we can try to maximize the Bhattacharya coefficient here, right? Now, let us look further on how we can do this. Okay, so if you take this Bhattacharya coefficient, which is given by this expression, I can write it as equal to this expression which is given here. Now, how we get this expression is, you can what you're making use of is the Taylor series expansion. So this is the Taylor series expansion general formula, where if I have, let's say, f of x, okay, and here I'm trying to find out what is the expansion about a point which is given at x is equal to a, then I can write it as f of a plus f dash of a into x minus a plus f double dash a by 2 factorial x minus a the whole square, and so on. Okay, so this is how you can expand using the Taylor series expansion. Okay, and here what we do is, in our particular problem, when you're using the Bhattacharya coefficient, okay, you're using the Taylor series expansion to expand it. Okay, but at the same time, you're taking only till the first derivative, and you're discarding off all that comes later. Okay, so you take only the first two terms over here and then try to simplify it. So when you're using the Taylor series expansion and taking only the first two terms, okay, the expression that you get would be this one, okay, as shown over here. That is, the Bhattacharya coefficient is equal to sigma u root of p u y n plus 1 0 p u y n. Now what is this p u of y of n plus 1 0? Now this one is nothing but an initial estimate, okay, which means that now again what I'm trying to do is I have an initial estimate, and from that initial estimate I'm saying that okay, my actual solution or my actual position where the circular domain has the perfect histogram match would be present somewhere near this particular position, okay, or somewhere near this y n plus 1. So that initial estimate from which or around which then you try to optimize the solution, okay, that is denoted here by p y n plus 1 0. So this initial estimate, you can use some other method to calculate the initial estimate, or you can also find the initial estimate by taking the previous frame's circular domain as the initial estimate. So what I'm saying is, again, as I said earlier, let's assume that you have one frame here and this is the next consecutive frame, okay, and this is the, let's say, the circular region of interest, and here this is the next circular domain where the object has moved, okay, or this is the translated vector over here, okay, and this here whatever you have, okay, that is my, let's say, the yn, okay, or where exactly the location is for the current frame, okay. Now what I'm doing over here is, now this particular location, this is going to be yn plus 1. So what I'm assuming here is that this is the initial estimate, okay, from which I try to calculate this is the initial estimate, and nearby this I try to keep looking for the regions or the similarity of the histograms, and then finally finalize with a circular domain with the maximum similarity. So for that initial estimate, to take that initial estimate, what you can do is you can assume this previous frame's circular domain itself as the initial estimate. Okay, so that would be like somewhere around here. So let's say this one, this particular one, okay, is my actual value, and let's say this one here is my initial estimate, that is yn plus 1 0, okay, 0 indicates the initial estimate. So from this initial estimate, it can just try looking at the neighborhood to find out the actual one, okay. So that is what this particular term indicates. So as I said, what we are doing here is we are trying to expand the equation here, and we try to retain only the first two terms. So you have these two terms as shown over here, okay. And further simplifying this term, what you get is the expression that is shown here. Just take the next slide. Okay, so again, this is the same as what we had shown in the previous slide. Okay, you have the first two terms, okay, and on simplifying, you will get it in this way. Okay, now what we see over here is that, let's say I'm taking this first term over here, okay. So when I take this first term over here, what I observe is that this particular, that is the probability density function of the initial estimate that I'm considering, and the probability density function of the previous frame, both of them are constants. Because see, this circular domain, whatever is being considered in the current frame, that does not change, that position does not change, that is always the same. Okay, so this is a constant factor, right? And pu of yn plus 1 0 is the initial estimate. Again, the initial estimate also remains the same, that does not keep changing. It is not the initial estimate that is changing. From the initial estimate, you keep trying to look at the neighborhood and then try to find the best match, right? So again, this also remains the remains a constant, or it does not change. So the only factor which keeps changing, okay, if you look, the only factor which keeps changing is basically this particular term, which is the second term. Okay, so what I do is what you're trying to do is you're trying to approach this as an optimization problem, right? So you're trying to maximize this particular coefficient or the LHS. So when you're trying to maximize the coefficient, okay, if you have constant terms over here which does not change, okay, with different values of, let's say, y, okay, because we are trying to find out the location y, okay, corresponding to which you want the maximum value, right? So these two does not change, so that means the first term need not be considered, okay, only the second term would contribute to maximizing the coefficient, okay. So I can say this particular term, that is half sigma u pu of y root of pu of yn divided by pu of yn plus 1 0, okay, over here. Now this is the term which would help in trying to maximize the Bhattacharya coefficient. So if you see over here, this term y keeps varying, okay. So the location of y over here, it keeps varying, okay, for different values of u. It keeps varying, and depending on this, you can try to maximize the Bhattacharya coefficient or the rho p of y, p of yn term here. Okay, so what we were discussing till now is how do we find y whose histogram is closest or similar to the histogram which is given at pyn. You have to find that value of y, okay, for which it lies the histogram is the closest or most similar to py of n, which is the circular domain in the current frame, okay. And in order to find that, what we do is maximize the Bhattacharya coefficient, and we saw that after doing a Taylor series expansion and taking only the first two terms and then further simplifying it, you can write it in this way, that is it is similar to just maximizing this particular term here, right? Now what we need to do, or we need to find, is how do we construct the histogram vector for the circle with center y, okay. Now how do we do that? So what we are doing is we are trying to track a deforming object, okay, and the pixels far away from the center may be quite different as compared to the pixels near it, okay. So what we are assuming is, let's say you have this is the image frame, and this is a circular domain that I have, okay, and this is the center, okay. Now what we are assuming is that those pixels which are closer to this center, okay, somewhere all here, all the pixels which are closest to this particular center contributes more towards the calculation of the histogram or the probability density function of the domain as compared to the pixels which are further away, okay. So making that assumption, what we how we exactly try to use this weighing factor is by making use of kernel smoother, okay. So in kernel smoother, what we are assuming is that we give more weightage to those pixels which are nearer to the center of the circular domain as compared to those pixels which are further away, assuming that, or under the assumption that those pixels which are nearer to the center contributes more to the probability density function as those which are further away, okay. So this kernel smoother is a concept that we have already seen earlier, right? If you remember, we had considered different kernels, the uniform kernel, the Gaussian kernel, etc. And using these kernels, what it basically does is, like for example, in the Gaussian kernel, if you observe, okay, here the maximum, let's say this is where the center lies, okay, corresponding to this particular point is where the center lies. So those pixels which are around and near the center would have, very close to the center, would have the maximum contribution, or we give more weightage to that as compared to those pixels which are further away from the center, okay. So this would be the kind of weighted averaging, or the weighted weights that we give to different pixels for the contribution of the PDF with respect to its distance from the center, okay. So what we do is, now each pixel votes into its bin in the histogram with a weight that decreases with the distance xi minus y according to the kernel profile. So it's basically the same thing, we're just assigning a weight over here, okay. Okay, So here what you're using is, as I said, we are using a kernel smoother, okay? And using this kernel smoother, the PDF, that is the probability density function of the circle, with the center at y is given by this particular notation over here, okay, pu of y. And this is the expression corresponding to that, where I have a ch, basically it's just a normalizing constant which is used. And here this term is something you are already familiar with, where I take the kernel, so this is a kernel function, and the kernel function is dependent on the distance between the data point and the center, okay, divided by h, which is basically the radius of the kernel, okay. And what you have is now an additional term, which is basically the delta function. We'll see what that is later. So as I said earlier, k is the kernel, and you can use different types of kernels as shown over here, again something that we have already discussed in the previous class. And the exercise that you here see are the different data points which is around the center, and y is basically the center, right? So here it is kind of a weighted what I say, weighted distribution of, or we are assuming different weights for the data points with respect to the distance from the center, okay. And the second term you have is del of b of fi minus u. Now, what this does is it will take the count of the histogram, okay, only if the feature vector matches with that of the bin number. Like what that means is, let's say you're assuming a particular histogram, and let's say the histogram looks okay. You're assuming different bins for the histogram, and let's say this bin is 1, this bin is 2, here 3, and so on, okay. So in this histogram, okay, this histogram center, okay, is given by whatever is given by 1, 2, 3, etc. Okay, that indicates my u over here, okay. And fi is basically looking at what exactly is the range or the feature vector value, okay. So if the feature vector value lies within this range over here, it would be assigned to 1, okay. Or if it is lying within this particular range, it would be assigned to 2, and so on. So depending upon the feature vector range, it would be changing, right? So the same thing is mentioned over here. That means it will take the count, or it will consider the count only if this particular fi lies within the range of u, okay. That means only then it needs to be given this count. So if you're giving a count over here, then for the rest of the bins you don't have the count, right? So either you have a count if the feature vector is near, or the feature value is near to the bin number, or you don't assign, okay, you just assign a 0 if it is not within the number. So what happens is, if you have the feature vector within the bin number, okay, then that means the histogram is incremented, and you have the probability density function, which is a function of the kernel, the weighted function, okay, or the weighted term here. The first term would exist, okay. Whereas the del of b of fi minus u, there you see that if the fi does not fall within the histogram bin, then this term would be 0, okay. So that means it is basically not in the bin, and therefore you don't have a contribution over there. Okay, so here once you have found the value of pu of y, okay, now what we do is we can substitute it in the equation which is present over here. So this equation, as I said earlier, you're trying to maximize the Bhattacharya coefficient. When you're trying to maximize the Bhattacharya coefficient, we saw that after Taylor series expansion and after discarding all the higher terms, what you have is only the second term which contributes to the weighting factor, and this is essentially trying to what we are trying to do is maximize this particular term, right? So if you just substitute the value that you got for the equation that you got for pu of y in the previous slide in this particular equation, okay, you will get this equation which is shown over here after simplification. You will get f of y is equal to ch by 2 sigma wik, and this is basically the distance, where this wi is given by the delta function into this particular square term that you have. Okay. So now again what happened is that our problem is now basically trying to, or it boils down to trying to maximize this particular function. Okay, and in order to maximize this function or this equation, we can make use of the mean shift procedure to maximize that. Okay, so this is where the mean shift procedure or the mean shift algorithm is helpful when you are trying to find the matching summary representation. So when you're trying to see whether two histograms are similar, or to find the position of the circular domain at which histograms are similar, then for that you can make use of mean shift procedure. And how or why the reasoning behind using this is where you assume the kernel smoother, and on substituting that on the equation or the second equation over here, we'll get an equation similar to this. Okay, and here this is similar to finding how exactly or where exactly are the dense points, because it is the dense points which basically contributes to the histogram, right? So finding the dense points and then calculating the histogram and looking at the similarity. Okay. So here, as I said earlier, now the problem now becomes maximizing the given function f of y. Okay, so after maximizing this given function f of y, so that means I'm trying to find out that value of y for which this particular function f of y is maximum. Okay, and as I said, you can use the mean shift procedure or the mean shift algorithm for that. Okay, and on substitution what you get is this particular equation of y of j plus 1. So the maximum value, okay, that you would get, the expression for y is given by yj plus 1 and this equation over here. Okay, so wi, as I said, basically it's trying to find out what is the histogram bin, okay, whether the feature contributes to the histogram bin, okay, and a ratio of the probability density functions. And here again you make use of the kernel functions or the weighting factor, where you say that the nearer the pixels are, the more the weightage. Okay, so this is the summary of the tracking which we were looking till now. Okay, that is the tracking by summary matching using the mean shift algorithm. Okay, so to summarize the same thing, what we do is we first take an initial estimate of yn plus 1 0. This initial estimate, it could be the same as the circular domain, the same location as the circular domain in the previous frame. That is one option, or you can use some other algorithm to find the initial estimate. Anyway, once you have the initial estimate, what is done is it would be within this near to this initial estimate that you try to calculate where exactly the histogram or the location to which corresponding histogram is the maximum, okay, or has the maximum similarity with that of the current frame. That is we try to determine that. Okay, and in order to do that, what we do is we make use of this final equation yn plus 1 to find out that value of y for which it can maximize the function f. Okay, so does anyone have any doubts till now? Okay, if there are no doubts, I'll move on to the next topic. Okay, I hope the PPT is visible. Now, we were discussing about different tracking methods, right? So broadly, it can be classified as tracking by detection or tracking by matching. Now, tracking by matching itself, it can be again subdivided into two different types where first one is where you try to track by summary representation or the summary matching. So in the tracking by summary matching, what you do is you try to locate regions of interest, calculate or give a representation of the summary of that region with the help of histograms, and basically you try to match the histograms and try to find out those histograms which are the most similar. So accordingly, that corresponding location would be the the new location or the translated point is what we are assuming. Okay, and like that we do it for all the corresponding consecutive frames that you have. Now, in the second type of method, which comes under the tracking by matching, is the optical flow method. Okay, so in optical flow, the basic concept is in this way. It is basically a 2D vector, okay, as shown over here, and it consists of optical flow vectors, which gives an information of how the pixels have been displaced between two different frames. Okay, so what we are assuming is, or what we are trying to say over here is, let us assume two different frames over here. I have frame one here, okay, I have a frame here, and I have the next consecutive frame here. So I'm considering two different frames which have been taken from a video sequence, let's say. And in these two frames, I'm trying to calculate, how much is the displacement, okay, which between each of the different pixels. So I'm looking at displacement of every pixel within the images, okay, and from that I get an information about how what is the movement pattern, okay, or how different objects in a given frame moves. Now, in order to do this, so let's say I have calculated the optical flow. Now, how the calculation is done, we'll see that later. So let's say such kind of an optical flow diagram has been created. Okay, so in such a case, what happens is it would look somewhat like this, where it's a 2D vector and it shows different arrows at different points. Okay, sometimes there are arrows, sometimes there are no arrows. So let's say in this particular figure, okay, this is not for the whole image, but only a part of the image has been taken for getting this optical flow diagram. Now, if you observe in this particular image, here this pattern represents this black car over here, okay, and this pattern over here represents the red car. Sorry, the white car, which is shown over here, right? So what you're trying to do is, or what the optical flow diagram says is, if you're trying to compare the black card from the first frame and the next frame, if you're comparing each of the pixels, okay, the card has moved, okay, it has moved in this particular direction. Okay, so these arrows represent where each of the pixels have moved, in which direction it has moved, that is shown by the arrows which are present here. And not just that, it also shows by how much distance it has moved. Okay, so what is this translation factor over here, or what is the distance, the magnitude or the displacement, magnitude of the displacement, how far has it moved, that also, that is shown by the length of the arrow. Okay, so in the optical flow diagram here, or the optical flow representation here, the each and every pixel, the motion of each and, or the displacement of each and every pixel is recorded, or it is calculated. Okay, and for each pixel it will have, the displacement will have the direction, which shows what is the direction in which the pixel has moved between two consecutive frames, and it also, the length of the arrow will show by what magnitude it has moved, okay, or how long, how distant has the pixel moved between two frames. So if you compare this black car, the movement of the black car, and the movement of the white car is shown over here, right? If you compare these two movements, one thing you observe is the direction in which the arrow is pointing is different. Here you see that the direction is upward, okay? It is somewhere around this particular direction, so which means that this car, okay, in the second frame this car is moving along this direction, okay? And you also see that the length of the arrows is less. So if the length of the arrows is short over here as compared to that of the black card, it is short here, which means that this is moving slowly with respect to that of the black card. Okay. Now, another thing you see in this diagram is there are a lot of regions where there are no arrows at all. You have all these regions here, all these regions here where there is no arrows which are present, okay, or there may be slight arrows which are very very small, okay. So in this image you do not really have much significant arrows. So what that means is that here in these regions there has been no displacement, okay, no displacement has occurred within these. So it gives us an idea pixel wise which are the places where there has been an displacement, which are the regions where there has not been a displacement, and if there is a displacement, by how much it has been displaced. So basically optical vector quantity, okay, is basically a vector which has got both magnitude information as well as direction information, from which we can calculate how much distance each of the pixels, it's a pixel wise information, each of the pixels has been displaced between two consecutive frames. Okay, now just give me a minute. I have we'll continue after 1 minute. Just give me a minute. Okay, sorry about that. We'll continue with the class. Okay, so we'll just look at some more examples over here, right? So corresponding to, let's say, a video sequence where a person is playing table tennis. This is an example of an optical flow vector. So why you see such dense regions is basically it's a pixel-wise calculation, right? And it also looks at the distance. So you'll have to exactly zoom in to see, the different differences over there. So from this overall optical flow, what you see is that this particular his hand movement, the region of his hand movement has the maximum displacement, okay, as compared to all the other regions. And if you're just looking at the background, you do not have any displacement information over there, because basically the background does not change much, okay. Being a video sequence, it can change, okay, but here there is not much of motion or movement pixel wise when you're looking at the object there, okay. And another example is shown over here again, where a person is playing, and the corresponding displacement information will tell us, which is the region of interest or the domain of interest where the movement has occurred. And it also gives the extra information. It's not just where the person has moved, or where exactly. It also gives a pixel wise information, okay. It gives a pixel wise information, and also the direction as well as the magnitude of the displacement is also obtained if you're trying to calculate the optical flow. Okay, so here this is just a video that shows, one such kind of a video sequence which we usually calculate, to find out how exactly the different pixel location or the pixel displacement happens between different frames. Okay, so you can assume that a video sequence may be somewhat like this, okay. And let's say you're looking at the position of the tree, okay, in this case. So maybe you're trying to track the position of the tree or so, okay. Or maybe there's some buildings over there. So when you're trying to calculate the optical flow, you'll see that between consecutive frames, the tree actually keeps moving to the left side, or the pixels have moved to the left side. So accordingly, the optical flow information gives the optical flow method gives that information of the pixel displacement. Okay. Now next what we'll see is how we can calculate the optical flow. Okay, so a video which is given, we've already seen that a video which is given can be represented in terms of different frames or images which are arranged along the temporal axis. Okay, so let's say if xy is usually the way how you represent an image. Okay, along with that, you can have another term here which is basically the temporal axis, and this denotes f of x y t denotes the video, right? And x and y are spatial coordinates and t is the time. Now let us assume that you have two frames in a video. So in a video, when you have two frames, okay, let's say the first frame is at the time or the temporal axis. If you're taking that particular time is at t, and let's say the next frame is at t plus dt, right? So what we are saying is this dt is not very small, because if you're taking just two consecutive frames, there is not much of time difference, okay, because typically there might be around 30 frames in a second. It can go up to 50 or 60 frames in a second, okay. So that means there won't be much changes in, or the dt, the value of dt will be small, and because of that there may not be much changes in the values or the pixel information which is present between two frames, okay. So therefore I can say the intensity at xy in frame 1 at time t will be similar to the pixel intensity which is present at x plus dx, y plus dy in frame 2 at time t plus dt. Okay, so that means after the displacement, okay, if I'm looking at the pixel location, after the after a displacement of dx along x direction and dy along the y direction, okay, let's say this is the particular pixel location in frame 2. Okay, so if I look at the intensity information at the location xy in frame 1 and compare that with the next frame, which is where the pixel has moved to x plus dx, y plus dy in the second frame. Second frame means which is at a time of t plus dt. Okay, what I'm assuming is that there is not much change between the pixel intensities in both the frames. Okay, because the time time is less over here, or you're taking a higher number of frames in per second. So there might be only very small change from x to x plus dx and y to y plus dy. This particular concept is what you call as the brightness constancy assumption. That means we are assuming that the brightness of the pixel intensities are or remain constant between two different consecutive frames. Okay, and this is expressed, this particular assumption is expressed in this way, that is I can write f of x yt, which is basically the frame, a particular frame in my video, can be written as equal to f of x plus dx, y plus dy, t plus dt. So t plus dt indicates that it is the second frame or the next frame which I am considering. T is the current frame, t plus dt is the next frame that I am considering. Okay, x plus dx is the location to which the pixel has translated along the x direction, and dy is basically the location or the amount by which the pixel location has translated along the y direction. Okay, and this is basically what represents the brightness constancy assumption, where you assume that to the pixel values or the intensities or the brightness remains constant between two different image frames. Okay. Now, having assumed the brightness constancy assumption, what you do is we try to again use the Taylor series expansion for this. Okay, so as I said here, this dx and dy means it is nothing but the pixel displacement along the x direction and the pixel displacement along y direction. And what that means is this dx and dy is basically giving us the information regarding the displacement of the pixels, which is nothing but the optical flow. Right now, in order to simplify this further and try to formulate that into a problem, okay, which can be solved solution, what you do is you can apply the Taylor series expansion over here, okay, in order to get an approximation of the function that you're using. Okay, so if you're using the Taylor series expansion, and as said in the earlier cases, we are assuming only till the first derivative, and you are discarding all the remaining derivatives that you're getting. Okay, this is a particular equation that you will get. Okay, so you have the first term, which is given by f of x yt, and the second term what you have is dou f by dou x into dx plus dou f by dou y into dy plus dou f by dou t into dt. Okay, now if you're on the second term, see the first two terms over here, f of x yt, f of x yt, these two terms are the same, so you can it kind of cancels out, and what you are remaining with is this term, right? You get dou f by dou x, the partial derivative of x of f along the x direction, plus partial derivative of f along the y direction, plus partial derivative of f along the direction t. Direction t in the sense, it is, since t is taken as one of the domain dimensions. Okay, the partial derivative with respect to t, this will equate to 0. So that can be represented in this simplified form. You're just changing the notations over here. You can represent this by fx dx plus fy dy plus ft dt is equal to 0. You come up with that. Okay, now what you can do is you can divide each of these terms with dt. Okay, so when you're dividing each of these terms with dt, what I get is basically I get it as fx dx by dt plus fy dy by dt plus ft dt by dt is equal to 0. So this dt and dt gets cancelled. Now dx by dt can be replaced by a vector which is given as u, and dy by dt we can let us replace that by a vector which is given by v. Okay, so if I do that, I get this equation here. I can get it as fxu plus fyv plus ft is equal to 0. Okay, so here u is what is the change in x with respect to dt, and v is what is the change in y with respect to dt. Okay, dt is nothing but the change in the temporal axis when you're going to the next frame, right? So basically this u and v are my optical flow vectors. Okay, so you can call these as the optical flow vectors, and it is this u and v value that I have to find in order to determine what is the displacement of each of the pixels in the frame, or when you're considering two frames. Okay, so remember that u and v are the optical flow vectors that I have. Now we need to find the unknowns here, right? So here the unknowns that we need to find is u and v. That means I need to find out what is the value of u and what is the value of v. Okay, because that would give me the information about whether there is a displacement, and if there is a displacement, how much is the displacement. So that will give me the motion information also, right? Now we see that there are two unknowns that has to be found, but there is only a single equation which can be used to solve to find the two unknowns, right? So in that case we cannot make use of the linear algebra equations to solve this, because you will need at least two equations to solve this, right? So instead of that, instead of using linear algebra, then what that means, we have to use some other kind of what we are basically doing is we will formulate this particular problem as an optimization problem, and then try to minimize it. Okay, so we'll come to that later. Now here, as I said, this is the equation that I have, right? The equation that I obtained after assuming the brightness constancy assumption, right? Now from this equation I can write this equation again as v is equal to, just rearranging it, I can write it as v is equal to minus fx by fu u minus ft by fi. Now if you observe this equation, this is somewhat equivalent to writing the it is a form of a equation of a line where I write y is equal to mx plus c, right? So y and x being the variables, right, and m or the slope, you can give it by minus, or you can represent that by minus fx by fi, and minus ft by fi represents the constant here. So if I rearrange this, I can write it in the form of the equation of a line, and what I do is I can try to plot this, okay, in a graph, and let us see how we can find the optical flow vector after doing that. So given this equation, v is equal to minus fx by fyu minus ft by fy, I can plot a line. So this particular line, okay, represents that equation which is corresponding to this equation, right? So what I do is I can just give a value. If I take u is equal to 0, I get a value for v. Okay, I'll get this particular point for v. If I take v is equal to 0 and calculate the value for u, I will get this particular point. And then if I join this, okay, I get this line. Okay, now what that means is, what I know for a fact now is, since you have a line which is joining this u and v, we can say that the optical flow vector that we are looking at, okay, would lie somewhere along this particular line. It would be located along this particular line, right? So so what we do is, again, as we said, there are two unknowns that you have, one equation, but only two, there are two unknowns, okay, and from the equation what we see is that we can calculate fx, fy, ft using the gradient operator at each pixel, because basically fx, fy and ft are the gradient information. But the problem here is that it is under constraint problem, okay, because you have only one equation and two unknowns, okay. But on plotting this, all that you know, or all that it can say is that the optical flow will lie along this line, okay. It can lie anywhere along this line. Now how do you find where does it lie? Okay, now in order to find that, what you can do is, you can assume that, let's say, let us assume that this particular point is where the displacement vector is, and it is given by the location u cap and v cap, okay. And this point can be represented in terms of two other vectors, which is basically vector D and vector P. Okay, so if I know vector D and if I know vector P, I know where exactly is this particular location, right? So I can say that this location of the optical flow vector can I can know that if I know the vector D as well as vector P, and this is basically D is basically the normal to this from the origin normal to the line over here. Okay, so if I know this and this. Now, what I see is that wherever is the point, this particular point, optical flow point, wherever it lies along this line, you see that the vector D remains the same. The value of D remains the same because it's basically the normal. The normal remains the same irrespective of where the position of the point lies within this line. So the only changing factor that you have is P. Okay, the value of P or the distance of this P over here from this point to here. Okay, that may vary. So for example, if you have an optical vector over here, now the value of P would be somewhere calculated till here. Okay, so the value of P changes with respect to where exactly it lies, whereas the value D remains the same, or it remains constant over here, right? Now you have certain names for that. D is what it is called as the normal flow, and P is called as the parallel flow. So if you are assuming this, now again another thing here is we need to compute P. Again, it boils down to trying to find out where exactly is this P, or how can you compute this P, because only if you know this P you can calculate the optical flow, right? Okay. So here, in order to solve this particular problem, Horn and Shunk has formulated this as an optimization problem. And what they did was they have introduced an additional constraint to the problem. Okay, and by adding an additional constraint, they have tried to approach the optimization in a better way, to try to find the optimal solution in a better way. Okay, so the additional constraint which they have put is basically the smoothness constraint. Okay, so what the smoothness constraint means is, I'll just show in terms of, okay, so let's say I'm taking this particular example once again, and in this, sorry, and in this example, okay, let me assume this particular region, okay, which is shown here. Now, in this particular region, so I don't need a big region. Let's say I'm taking some small region. Okay, if I'm taking a small neighborhood region over here, okay, what I'm assuming is I'm putting a smoothness constraint which says that the optical flow vectors which are present in this neighborhood, okay, or within this neighborhood is similar. Okay, so smoothness means that it is the optical flow vectors are similar within a small neighborhood. So the constraint here is that considering a small neighborhood, it remains the same. So that applies here also. Now let's say I'm taking a small neighborhood here. So within the neighborhood, if I'm assuming all the optical flow vectors, then here also you see that it is the same within the or it is more or less similar within the neighborhood. So wherever you take the neighborhood, let's say I'm taking it here, I'm taking it here, or I'm taking it here, in all these regions you see that the optical flow vectors are similar, and therefore I say that this particular region is smooth, or this particular neighborhood is smooth. Sorry. But there are, you can't say that it would be the same for the whole of the image, because there are regions, for example, if I take this particular neighborhood, okay, in this particular neighborhood, what I see is that this pixel has got this information, there is a displacement information, but the remaining pixels over here do not have that information. Or let's say I'm taking an example over here, where I have a displacement information for these pixels, but there is no displacement happening along these pixels, which is towards the left side. So if you look at certain regions within the kind of the boundaries of the objects, okay, if you're speaking in terms of the images, in these regions you do have some regions where the smoothness constraint is not valid, or the region is not smooth, okay. Except for those regions, what we say is more or less, if you're considering the whole image, okay, if you're taking a small neighborhood, the smoothness constraint is satisfied in the sense that the optical flow vectors which are present within a small neighborhood is the same. Having or what they did was they put that particular constraint, okay, which is known as the smoothness constraint. Along with that, they have also assumed the brightness constancy assumption. So brightness constancy assumption says that if you are considering two consecutive frames, then for a particular pixel location intensity after translation, it has moved to, let's say, a dx dy position, but the brightness remains the same for both the frames, right? And we also saw the formula for that. So along with that assumption, it is also putting another constraint, which is the smoothness constraint. So having added this smoothness constraint, what we are doing is they have formulated this equation. We are trying to minimize this particular equation, which is shown here, right? So in this equation, minimizing this particular equation would give us the optimal solution, is what has been proposed or formulated by Horn and Shank, okay? So in the expression, if we see, so what we are trying to do is, what we are trying to see for which values of u and v being the optical flow vectors, for which values of u and v will we get the minimum for this function. So what that means is, if let's say I'm assuming, what I say by the minimization problem is, if I'm assuming there is a function which is given by f of x, okay, in this case, let us assume that this whole function is given by some f of x, and let's say if it is along a particular variable, one particular variable, then what is the value of x at which the function f of x will give me the minimum value, right? Now in this case, you have two different variables. The variables that you're trying to minimize, or the optimal solution of which you're going to find, is uv. So what we are saying is that what is the value of u and v corresponding to which this whole function over here gives me the least possible value, okay, which is given by this minimum value, then that would be my optimal solution, right? And for this minimization problem, as I said earlier, they have added a smoothness constraint. So this is basically my smoothness constraint term, the term which represents the smoothness constraint. So if you look at the first term, this first term is something which is already familiar to you. You have fx u plus fy v plus ft. That means the partial derivative along the x direction into u, right? So here, this is basically corresponding to the brightness constancy assumption that we considered in the first case. Okay, that is my first term. And the second term is basically from this ux square plus uy square plus vx square plus vy square is basically the term that represents the smoothness constraint. Okay, now here, each of these terms. So what ux means over here is, it is basically the gradient of the optical flow vector u along the x direction. Y would be the gradient of u along the y direction. Then you have the optical flow vector vx and vy. So basically you're taking the gradient along the x direction and y direction for the optical flow vectors. Okay. So what I'm saying is, when you're trying to introduce a smoothness constraint, what you're basically doing is you're just trying to find out the gradient of these optical flow vectors along the x direction as well as y direction. So if the optical flow is smooth, okay, that means if let's say around a particular region, when you're taking all the optical vectors, let's say all are having the same magnitude and direction, what happens is that means it is a smooth region. So there won't be a gradient information when you're trying to calculate the derivative, or when you're trying to calculate the gradient over here, there won't be an information. So that means you'll get a 0 or somewhat a very low value over here, right? But if it is not smooth, like for example some cases which we have already seen earlier, okay, it may not, the gradient would not give you a 0, but it will, the gradient would give you a 0 as long as the smoothness constraint is satisfied, or the optical flow vectors are uniform throughout the neighborhood that we are considering, okay. So since we are trying to minimize the problem, what we are doing is we are trying to find the gradient and trying to minimize that, okay. So we'll do one thing, we'll stop till here and we'll continue in the next class. So do you have any questions till now? Okay, so if you have no questions, then it is time for conducting the quiz. So I will post the quiz within a few minutes, and I'll just continue the meeting also. So once the quiz is posted, as I said earlier, it would be 2 MCQ questions and you will have to submit it within 5 minutes. Try to stick to the time and submit it within 5 minutes. And I will keep the meeting on till the quiz has been posted.